For our second talk, we're very happy to have Gustavo Salinas here to tell us about gravitational waves in dark sectors.
All right, thanks John and Cody for organizing this seminar series. So as John said, I'm going to talk about gravitational waves and models of dark sector confinement. This is a work with Jim Everson, Cody, Anindita Maiti, and Brent Nelson. So as you probably noticed from the title, the word pheno should be much bigger than the word string for my talk. String only comes here as the motivation for the pheno. So I'll first introduce gravity waves and describe how they can be produced in phase transitions. Then I'll describe how you can model Pure-Yang-Mills dark sectors by mentioning some facts about lattice thermodynamics and describing the symmetries of the model along with some group theory. Finally, I'll show how to calculate the gravity wave signal from the confining phase transition, which are the possible sources, and how the cosmic evolution of the universe is relevant for the signal, and also describe future experiments. All right, so when you talk about gravity waves, you typically have two types of signals. The first one are signals from single events, such as black hole mergers or interstellar mergers. And as you all know, this is what has been seen in LIGO. But you can also have stochastic signals of gravitational waves, which are much like the CMB, but for the gravitational interaction. Now, these can be produced by topological defects, such as cosmic strings, by inflation, or by cosmological first-order phase transitions, which is the topic of this talk. So with the first-order phase transition, you have a potential, you have your false vacuum, and you want to tunnel or transition to the true vacuum, but there's a barrier in between them. This makes a range of temperatures for which you have both the symmetric and the broken phase existing simultaneously. The transition can happen via thermal fluctuations or by quantum tunneling, depending on the action for this tunneling solution. Some energy is produced, some latent heat, that makes bubbles of the false vacuum nucleate, and then they expand until they collide and produce gravitational waves by the collision and by the subsequent motion of the plasma after the bubbles collide. These transitions do not have to be in the dark sector. For example, in the standard model, you have the electroweak phase transition and also the QCD phase transition, but they're only first order in extensions of the standard model. So you only get a significant gravity wave signal if the transition is first order. So this is my only stringy slide. So in many cases, it's common to have many dark gauge sectors in string theory, and you can kind of consider the confinement scale as a free parameter. It's determined by the geometry, but it spans many orders of magnitude. For example, in F theory, you have many geometrical gauge sectors that are forced to you by the geometry, and these typically have many gauge factors. An example is the tree ensemble, which was built by some of my collaborators, which has a minimal gauge sector that's given by a bunch of these factors, dozens of E8 factors, F4s and G2s, and some other gauge groups as well. So you have hundreds to thousands of factors, gauge groups in these constructions. Many of these sectors are going to be Pure-Yang-Mills, so they have no matter. So above some critical temperature, at high temperatures, you have dark gluons that are free. Once the temperature goes below this critical temperature, these confine into glueballs. This transition is first order, is known to be first order or expected to be first order to most gauge groups, and these are going to produce gravity waves. Now, the order parameter for this transition is the Polyglot loop in the fundamental representation. It's given by this lowercase l, and is related to the trace of the Wilson line in the thermal direction. So you get the time component of the vector potential. Physically, it's related to the energy of a pair of a quark and an antiquark, which are very heavy. So if the energy between this pair is infinite, you are in a confined state, and this order parameter is 0. If it's not infinite, you are in a deconfined state, and you can get a VEV for this order parameter. Another important concept here is that of center symmetry. Because the order parameter changes under the center, if you are the confined state, center symmetry is preserved. But the deconfined state spontaneously breaks this symmetry. This symmetry was previously thought to be necessary for confinement. However, G2 has a trivial center, and it's seen to confine on the lattice. So there's something else going on here. A little bit more about the region above confinement. So the perturbative vacuum at very high temperatures has order parameter 1. But what you see on the lattice is that right above the critical temperature, it does not go directly to 1. So it jumps from 0 at the confined state to somewhere between 0.4, 0.5, and then it continuously grows until it reaches the perturbative vacuum. So physically what's happening here, you don't have a fully deconfined gas. There's still some strong interactions between the gluons. And this region is called the semi-quark gluon plasma. So it's intermediate step between the perturbative vacuum and the confined state. These are the groups we have lattice data from for the order parameter. And you can see that they all fall in this purple region, which we call the expected region, as we want to extend that to other gauge groups. Other thermodynamic quantities are also important here. First one is the pressure. So it grows from almost 0 at Tc to 0.7 of the ideal gas value at 2 Tc. But more importantly, this combination, energy density minus 3 times the pressure, which is called the interaction measure, it seemed to be proportional to T squared on the lattice. So if you plot delta over T squared, you have a plateau. And also the value of that plateau per gluon is almost the same for all the gauge groups. There is data on the lattice. Now, if you go to high temperatures, you can calculate this quantity, and the perturbative contribution is much smaller than what's observed on the lattice. So you can think of this quantity as a window for non-perturbative physics happening close to confinement. If you want to describe that in an effective model, you have to add a term in the effective potential that is proportional to the temperature squared. Okay. So the simplest effective model you can build is just the potential of your order parameter, which these are called the Polyglot loop models. It can, for example, explain why the transition is first order for SU3, but it fails for larger number of collars. As we want to extend this to other gauge groups, you have to go a little bit further and consider something that is called a matrix model. So instead of the order parameter being the variable in the potential, you go one step back, and the Wilson line itself are the variables. The eigenvalues of the Wilson line are the variables for your model. So you can think of going as the domain is going from your gauge group all the way down to the Lie algebra as your domain. So for simplicity, you can consider a constant background field in the time direction. You can diagonalize this by gauge transformations. So you can bring this guy to the Cartan subalgebra of your Lie algebra. Once you write this in terms of a basis, you can choose this basis specifically such that these QIs, the numbers multiplying the basis, are related to the simple roots. So geometrically, these coordinates are the distance between the point in the Cartan subalgebra and the borders of the so-called Weyl chamber. And we're going to write the potential as a function of these variables. The perturbative potential can be calculated. So one loop order is given by a constant here plus a term that is polynomial. And this B4 is called the Bernoulli polynomial of order 4. The sum here runs over all the roots in the root system. And just by looking at the perturbative term, the minimum occurs at the 0 of the algebra. And this means no confinement. All the eigenvalues of the Wilson line are 1. So they just collapse to a single point in the unit circle. So to describe confinement, you have to add something. You have to add a non-perturbative term. For example, for SUN, the confined phase has all of these eigenvalues uniformly distributed along the unit circle. So this non-perturbative term has to generate eigenvalue repulsion in order to describe confinement. There's also symmetries that you have to impose for that potential. One of them, as I mentioned before, is center symmetry, but also Weyl group invariance, which is something that is built in the Lie algebra, is the group of isometries. And this consists of reflections about the hyperplanes that are perpendicular to the simple roots. So these are these dashed lines here, reflections about these dashed lines here. These symmetries imply that the variables I constructed before have to be periodic with unit period. All right, so for SUN, for example, all the simple roots have the same length. So once you do these Weyl reflections, they generate permutation of all the roots. So if you want to construct terms that are invariant under the Weyl group, you have to sum over all the roots. And we're going to take polynomial terms here. Or you can also sum over pairs of roots and so on. Another symmetry that you can apply here is that if you combine a Weyl transformation with the periodicity, you have that the potential has to be invariant under variable going to 1 minus variable. And the Bernoulli polynomials have this property here. So if you choose your polynomials to be Bernoulli polynomials of even degree, they are the building blocks for these terms. Right, so we construct the non-perturbative potential as such. The t-squared term is where we put all the dynamics. So these are the terms that generate eigenvalue repulsion. We also add a constant term that doesn't depend on temperature. This is usually termed the bag constant, and it's used to fit the latent heat from lattice. But we also add another term in order to fit the correct Polyglot loop from lattice. And this is just added by hand to fit the lattice thermodynamics. Now, as I mentioned in the previous slide, these terms V1, V2, and V3, they're constructed from the symmetries. And we go up to order 4 for the polynomials, because this is the smallest order you can use to describe the transition. Of course, there are constraints. The phase transition has to happen at the critical temperature by definition. And also the pressure has to vanish in both the symmetric and the broken phases at confinement, as seen on the lattice. It also has to reproduce the latent heat from lattice. once we apply this, these 6 coefficients go down to 2. And we use that to fit the curves that I shown before, either to lattice or to these expected purple regions. All right, this is the result of the fit for the interaction measure, SU3, SU4, and SU6, and also for the Polyglot loop. You can use a simplifying assumption, which is termed in the literature the uniform eigenvalue ansatz, which is pretty much assuming that the points where the minimum of the potential occur is equidistant from the faces of the Weyl chamber. And this is enough to give you a good fit to lattice thermodynamics. So a similar story happens for G2 and F4. And again, we take these motivated by string compactifications. The story is a bit different because now you have short roots and long roots in the set of simple roots. So because the Weyl group is composed of reflections, they can only permutate short roots or permutate long roots to have a little bit less symmetry. More terms are allowed, so your effective potential gets a little bit bigger, but you can still fit to either lattice data or expected lattice regions. And here I have a bunch of curves for G2 and for F4. These change by the choices of confined and broken phases at the phase transition. The only thing I'm imposing here is that the order parameters are correct at these points, but for G2, for example, you can have any point in this region for the point right above the transition and any point in this line for the confined state. All right, once you have a model, there's a standard procedure to calculate the gravity wave signal. These depend on a bunch of parameters. The first one is this parameter alpha, which is the energy that is liberated in the phase transition, normalized by the thermal energy in the plasma at the time, or the total radiation energy of the universe at the time of the phase transition. And this temperature Tn is called the nucleation temperature, which is the temperature that you get one bubble nucleated per Hubble volume. And in our case, this is very close, a little bit below the critical temperature. Another factor that is important is the Hubble parameter at the time of bubble percolation, which for us, it's also very close to the nucleation temperature. So all these three temperatures are very similar for us. The inverse duration of the phase transition is given by this parameter beta, where this action here is the action of the bounce solution between the two minima. So if you get this parameter to be order 10 or 100, you can consider this to be a long-lasting source of gravity waves. If they are much larger, this is a fast transition, so you have a smaller signal of gravitational waves being produced. And finally, you have the bubble velocity, which is the terminal velocity for expansion of these bubbles, which we take to be relativistic. Now, for the confining phase transition, both the pressure and the energy density are approximately 0 below the phase transition. The pressure is also 0 above the phase transition, but the energy density jumps discontinuously. If you plug all that into the alpha parameter, you get 1/3. If you assume that the dark sector dominates the energy density of the universe at the time of the phase transition. If you don't assume that, you get a smaller signal, a smaller alpha, which implies a smaller signal. So to get the maximal signal possible, we assume 1, but this is going to be an upper bound for the signal. So then you proceed, you have the action for the bounce given by that. You can find the nucleation temperature by this condition here when the action divided by the temperature is order 100. And this is enough to find the parameter beta. And in these confining models, we find them to be order 10 to the 4th, which fit this fast category of phase transitions. So how are gravity waves produced? So the bubble collisions produce gravity waves, but these are negligible for these types of bubbles, which are called non-runaway. And these happen to be the case for us. Non-runaway bubbles are when the friction that the bubble experiences is non-negligible. And then we're left with sound waves and turbulence contributions. The sound wave contribution is given by this. This is the energy density produced in gravity waves. So K here is the kinetic energy fraction that goes to the bulk of the plasma. R star is the size of the bubbles when they percolate. It's related to the parameter beta and the wall speed velocity. This is given by numerical simulations, and the spectral shape is just the shape of the signal in frequency space. And there's a peak frequency, which gives you maximal signal. The turbulence contribution is subleading. It's a similar order of magnitude, but a bit smaller, and it's given by a similar formula. The peak frequency is a bit higher than the sound wave contribution, so you're going to see a double peaked spectrum. Now, this factor FGW that I didn't mention, it accounts for the redshift from the production of gravity waves all the way down to today. So once you have confinement in a dark sector that's dominating, the glueballs are now going to start to dominate, and they behave as matter. So you're going to have an early matter domination phase. We know that these glueballs should decay before BBN, otherwise the predictions of BBN are contradict. So also this matter dominated phase suppresses the gravity wave signal. So we're going to assume that the glueballs immediately decay after the phase transition to see what the maximal signal is. But if the glueballs linger for a little bit, it decreases the signal. And just some other parameters. After the glueballs decay, you have the temperature in the visible sector, radiation as T star V, with G star V relativistic degrees of freedom. Now, this is the resulting spectra for SUN gauge groups. As you see, LISA, which is the next generation search, is all the way up here. So you are many orders of magnitude below LISA. But there are more futuristic experiments such as BBO and DESIGO that are sensitive to these signals. SUN could be also plotted here. It would fall exactly on top of SU6, which is expected because 6 is on the lattice is already n infinity, so not much difference there. And these bands are given by a value of the coupling constant, the dark coupling constant at confinement, varied between 0.1 and 0.5. All right, so for G2 and F4, you get a very similar signal. But there's these bands are a bit larger because other than varying the confinement, the coupling, you get those different choices for the confinement point, the confinement phase, and the phase after the transition. So there's more theoretical uncertainty here, but the order of magnitude is similar. If you vary this temperature of the photon bath after the decay, this signal just walks horizontally up and down. the peak frequency is directly proportional to this t, so it can get in and out of this observation range. So almost done. As I mentioned before, this signal is many orders of magnitude below next generation experiments like LISA. And this suppression is has been recently observed in other effective models of phase transitions, with these values beta 10 to the 4 being somewhat common. However, these future searches might be able to see the signals. But the lesson we can take from here is that if you have many of these dark sectors, all of them could be confining, but they're not super noisy gravitationally. And it seems that going to even larger gauge groups does not seem to change this. I have some preliminary data for E8. The spectrum seems to be even lower. So yeah, so summarizing, you can have many pure Yang-Mills dark sectors in string theory. The thermodynamics of this transition can be described well enough in an effective model. We can assume that the gauge groups will have a similar thermodynamical behavior, motivated by what we see on the lattice. What differentiates the gauge groups are the symmetries. The structure of the Lie algebra makes the effective potential different. The gravity wave signal is produced, but it's not nearly strong enough to be visible by LISA. And if you, in the early universe, reheat many of these dark sectors, the suppression gets even worse. These, however, might be accessible to futuristic experiments like DDO and SUGN. That's all. Thank you.
Great. Let us thank Gustavo for his very nice talk and see if anyone has any questions. While we wait, I am a little confused about the fact that the signal does not seem to scale with the number of degrees of freedom of the gauge group. Is there like an intuitive explanation of that fact?
This goes back,
especially like SU3 then bumps up to SU4 and then bumps down to SU6. Like that.
Yeah, I think this behavior is mostly due to the noise in the lattice data. For SU4 and SU6, they are pretty noisy. So I wouldn't take this ordering very seriously. It's just more order of magnitude calculation. But to answer about the size of the gauge group, if you look at this parameter alpha, it pretty much gives you the ratio of whatever energy is liberated in the transition, but you divide by the total energy in radiation. So if you have many degrees of freedom, the energy that's liberated is proportional to the number of degrees of freedom, but you have to normalize by the total radiation energy in the plasma. So you pretty much get a ratio that is not dependent on the number of degrees of freedom. Yeah. So the signal gets higher and lower depending on how fast the transition is. You want it to be very long lasting, and these all seem to be quite fast.
Yes. Andre?
Yeah, I was wondering, in a string context, you would probably assume that a lot of these hidden sectors would be n=1 super Yang-Mills theories. So was your analysis actually including gauge genus, or was it really just pure gauge theory?
Yeah, it's just pure gauge theory. So we're imagining that the gauge genus are messed up by SUSY breaking, so we're below that scale.
Right. SUSY breaking by gauge genus condensation.
Yeah.
But that's all happening in the same sort of package, isn't it?
Yeah, but it could be in a different sector, I guess.
well, that would only be transmitted gravitationally to the sector you're interested in, and the suppression would be down by a power of Planck mass. So
yeah.
Yeah, I mean, it was very interesting, but maybe in the string context, what you have to do is actually to try to include gauge genus, I would imagine.
Yeah, maybe yeah, I agree.
Okay, well, if there are no further questions, let us all thank both Callum and Gustavo for the very nice talks, and we'll see everyone next week.